Hi everybody, my name is Mohamed Mahgoub. I'm the program director of a program called Concrete Industry Management. I'm doing this presentation. With me is my ex-PhD student Mohamed Hussein. He's working with New Jersey Department of Transportation right now. And we're going to talk about biochar and how concrete is becoming a carbon sponge. Again, as we heard from the first two presentations and some introduction in the third and the fourth presentation about the biochar, we are in an era of climate change. Everything is changing. As you can see, in the last couple of 100 years, we are getting sometimes we are saying global warming, sometimes we are saying it's getting cold, sometimes we are saying El Nino, El Nina, all of this stuff. We think that this is a big problem, and most of those problems are due to the carbon, CO2 in the air. So the climate change, as we can see here, that the number 3 times is the number of climate-related disasters, tripled, and we can see, you can hear every a couple of weeks about a new disaster everywhere. And actually the Myanmar earthquake, which happened a few days ago, and that was the worst in the, my master's and PhD is in earthquake engineering, 7.7, this is something very, very catastrophic, especially as you do that Richter scale is algorithmic scale. 2.5, the rate of global sea level, the rises between 2006 and 2016, faster than all of the 20th century. 45 million drought is in Africa. More than 45 million people are struggling to find enough food across 14 countries. 110 billion damage from the 2019-2020 Australian wildfire. We hear wildfire everywhere, especially the one happened in California recently. So this is a $110 billion cost. Since 1980, 396 weather and climate disasters were overall damages past $1 billion. Total cost of approximately $2.78 trillion, which is about 63.2 billion per year. New annual record of 28 events in 2023. And that picture over there is Helen hurricane, which happened in like few months ago, September 2024, and the damage was huge. And it went, as you can see, from south to north, passing by North Florida and the Carolinas. And this is a picture of the damage, as you can see. World produces 37.4 metric tons of CO2 each year worldwide in 2023. U.S. emission in greenhouse gases in 2022 amounted to 6.3 billion metric tons. Transportation industry is suffering, actually responsible for 28% of the greenhouse gases in U.S. And the global framework, we would like to reduce the impacts of the climate change by limiting the warming to well below 2 degrees and pursuing efforts to make it even 1.5 degrees Celsius. I remember, I live in New Jersey. I used to live, by the way, near Toronto here. I got my master's from McMaster University, and then I moved to Ottawa, so the snow is everywhere. It was snowing even last week. I was there. And I live in New Jersey. I don't remember I put any salt in my driveway in the last 2 winters. And this was something we have never, I have been in New Jersey for like about 15 years. This is something very strange. So there is global warming, no doubt about it. So U.S. is committed to reduce the greenhouse emission by 26% to 28% below 2005 levels by year 2025. Concrete, as we heard before from one of the presentations, that it's the second most widely used material after water. This is the first human-made material used. And the global annual production of concrete is about 500 billion cubic feet. And the concrete produced annually could pave a 1-lane road to Mars. Cement, of course, is the key ingredients of the concrete. And cement accounts for 8% of CO2 emission on the global level. And as you can see here, this is a picture of the contribution during the cement manufacturing for the CO2 from one stage to the other. And that, by the way, they always blame the cement on the CO2 emission, although that there are other factories. And the car muffler even is emitting more CO2 than the cement. And plus, the concrete is absorbing back some of those CO2, about 50%. So if the cement industry is producing that 8%, but the concrete is going to take it back, take half of it back. This is a graph from one of our papers published about lightweight concrete. It shows that the CO2 emission in by 1 million tons globally and in the United States. And you can see that the numbers are increasing between year 1960 to 2020 for the global, and we can see that the United States are doing their best, although that people are still fighting that global warming and this stuff, but we're doing our best to reduce the CO2 emission compared to the global effort. CO2 concentration has been steadily increasing globally since 1960. Major greenhouse gases, CO2, methane and nitrous oxide. CO2 traps heat in the atmosphere, leading to global warming. So this is the supplementary cementitious material. This is the coal, fly ash coming from the coal industry, and blast furnace slag coming from the iron industry, and then silica fume coming from ferrosilicon. And again, the challenge is our job. We cannot work from home. We have a concrete lab, and the students have to work in the concrete lab. They cannot produce concrete at home, and this is why we are working 24/7 to produce the concrete. So we have to reduce the CO2 emission at the same time as meeting global demand. Global cement production will grow up by 23% to 23% by year 2050. 10 gigatons of CO2 would need to be sequestered annually for the next 30 years to meet climate goals. The biochar, and as we heard in details, that the biochar is high carbon solid, eco-friendly solution by converting waste material produced through pyrolysis, and we heard that of organic material, widely recognized for the stability to improve soil health and other things. And again, biochar sources, as you can see, it can come from different sources, from rice husk, rice hulls, as we heard before, from wood, from sludge, from straws, anything that we burn. And I had another previous presentation. We were talking about burning, getting the biochar from burning some type of flour raising on the top of the Nile River in Egypt. And this is another thing of biochar. You burn anything, and then after that it's full of carbon, and you use it. And here is the biochar, the sizes ranging from very fine to coarse. And this is the process of the biochar, starting from beginning to end. And we heard about this, but you see, as you can see, the output is biochar and biogas and bio-oil and the heat and electricity. So as we can see here, this is the process. I'm not going to go through this in details because you guys heard people better than me in discussing the biochar material and what's the input and what's the output. It's used in the transportation application, composting and soil stabilization. We heard that, carbon sink and water treatment as well. So all of those used are in the biochar. And then the carbon capture is biochar serves as a carbon sink by absorbing carbon from the atmosphere and put it underground. And it was able to suck 23% of its weight in carbon dioxide from the air while it's still reaching a strength comparable to ordinary cement. then we are going to move to the concrete. Since I am a concrete guy, then what are we doing with the biochar, adding it to the concrete? What is the effect of that? So we started a long research sponsored by a company based in the United States, but it has the main branches overseas in India, and they are doing the rice hulls a lot in India. So we got the biochar from there, which has about 60% carbon in it, and we got that biochar from them, and we said we are going to do it because they wanted to expand their production here in the United States. They were doing just pantries and embankment and stuff, and they would like to know if we can do structural elements using the biochar. So we said that's fine. We are going to start with doing the compressive strength and all of this stuff. So and it's a long process. I was expecting that we are going to finish it soon, but actually the funding problems and stuff is delaying it a little bit. As you always know the situation right now. So the objective of the study is to utilize the biochar as a partial replacement of aggregate in concrete production, and to assess the practical feasibility of biochar incorporating in concrete in real world, and reduce the environmental footprint of biochar while maintaining the concrete integrity and characteristics. So we went to the New Jersey Department of Transportation, and we focused on Class B, which is the main class used in the building, in the concrete buildings. That Class B, it has the design strength of 3,700 psi, 28 days, and they have something in New Jersey DOT called verification strength. To get that design, they said, no, we need to break the cylinders on higher PSI to make sure that we are going to reach, or we are going to be in the safe side, because there are lots of uncertainties when you breaking the cylinder and putting the concrete in reality in the structure itself. So there is verification strength, which is a little bit higher than the design strength, and there is maximum water cement ratio, which is 0.488, and the minimum cement content, which is 564 pounds per cubic yard. So we did, again, as we heard before, we did a 100% Portland cement specimen, and those are the characteristics of our specimen. We have fly ash, we have coarse aggregate, of course normal fine aggregate, and then the biochar and water, and the water cement ratio, and those are the specific gravities on the side. And we wanted to check the concrete properties, workability, air content, density, and strength. We started with those things, and we said we are going to do replacement by weight to fine aggregate, and then replacement by weight to cement. We did the fine aggregate. We are working on the cement right now, but we didn't get the results yet. So it's promising results, but not included in this presentation. Of course, we followed the fresh and hardened concrete tests from ASTM, slump and air content and density. And we did the compressive strength 7, 21, 28, and 56 days. So this is the test results for the slump. And this is the, on the left-hand side is the mix, which is the base mix. And then after that, we did the replacement by weight again for fine aggregate, 5%, 10%, 15%, 20, 25, and 30% fine aggregate by weight. And we can see that the slump is increasing by increasing the replacement of by increasing the percentage of biochar replacement. The density, as we heard before, that the biochar is a porous material, so we are expecting that the strength, the density is going to go down from 150 to about 117, 18 when we increase the replacement, fine aggregate biochar replacement to 30%. This is the air content, and I see some anomalous, two anomalous points, but we are expecting the air content increasing by increasing the slump replacement for the fine aggregate because of the voids. The voids are more, so we are increasing the air content at the specimen. So we have a couple of anomalous points here, which is, those are the bottom points, but we put them in case. So here, the 7 days compressive strength, and as we can see, the solid black line is the line which is the design compressive strength for NGDOT, and the dotted line is the verification strength. So this is the 7-day compressive strength in PSI, pound per square inch, and those are the replacement until 30%. This is the 14-day compressive strength, and we did the 21-day compressive strength, and we see that we are getting higher. 28 compressive strength, we are getting higher up to almost 15%, and then after that everything is collapsing, going nose down after that. This is the 56 days compressive strength, again up to 15%. We are in the safe side. 15% is on the verge, and then after that everything is going down. So this is the compressive strength comparison to the base mix. This is mix 1, which is 5%. 2 is 10% by weight, and then 15 and 20, and then 25 and 30. As you can see, this is 7 and 14 and 21 and 28 and 56 days cylinder strength. As you can see, it holds steady for 5%, and then it goes a little bit down 10%, and then on the verge going down at 15, and then after that it's way down, and it's not achieving, it's less than 100% compared to the base strength. So as a conclusion of our study, and we still have more results, but I don't have them right now, and this, by the way, we would like to thank CSIT, Commission for Science and Innovation and Technology, Science, Innovation, Technology. This is a big organization in New Jersey to fund this research, and the company who gave us, donated the biochar is a company called Solace, and it's originally based in India. So the conclusion of this study is that the biochar absorption varies due to material source differences, as we show that it varies because of the source. And actually I received last week a biochar sample. They said that it has minimum 90% carbon on that, so that the factors are endless. So I would like to try this 90% biochar. I don't know how much is the cost of it. I think it might be higher, but they said that your biochar 60% is very low, so try the 90%. So we are still open for all the factors and all suggestions. Biochar concentration 15% as a fine aggregate replacement have met or exceeded the strength requirements, and high biochar content as partial replacement for cement, which we are working on right now, and fine aggregate has many lower strengths applications. As we said, if you do them, you can do the pantry and all of this stuff, non-structural concrete. High quality biochar, the 90%, yeah, and this fly ash produce lighter, stronger carbon, and that's why I received actually, and I'm pretty sure that it's going to be that. We have promising results we did 80, but minimum 90 we didn't try yet. Internal curing of biochar assisted the cement hydration process by absorbing and releasing the water. We use, of course, high range water reducer, of course, because this is gonna make up for because when we started, the biochar absorbs all the water, and even the drum was not even rotating smoothly because the biochar absorbed everything. So, and we were like, what's this? This is a very like water absorbing material, so we have to increase the HRWR. A water reducer is recommended to counteract the biochar's higher absorption rates, and the higher biochar content increases air content levels and other stuff, and as we saw in the pictures. So in the works, cement replacement by fine biochar, which is well grinded biochar, and both fine aggregate and cement aggregate replacement. And then we would like to do the life cycle analysis, and there is the part of the cost, because we see that it's like FRP. The cost of FRP in the old days, it used to be expensive. Now it's cheap. It seems the biochar is going the same way. It was expensive and now it's getting cheaper. And then in the work as well, the durability assessment of the cement replacement and both fine aggregate and cement replacement. I think that's it. So if you have any questions, I would be more than happy to answer. Thank you.